Hello viewers, I welcome you all back to this module to discuss about the methods of extraction. In our previous modules, we have discussed about the principles and different analytical systems which are involved in the solvent extraction process. In this particular module, let us discuss about what are the different methods we will use while extracting the solutes in liquid-liquid extraction. Methods of extraction are very important in order to understand which liquid-liquid extraction method has to be followed for the extraction of the solutes which are present in various quantities. Suppose you take a sample in which the analyte is present in very minute quantity. What is the extraction technique we have to use? And if you take the sample, it is containing the analyte in more quantity, that is say in milligram level, say 10 milligram, 50 milligram, 100 milligram, or even 500 milligram, etc. What is the extraction technique we have to use? And if the solvents which are yielding the extraction efficiency which are very high, how many extractions we have to perform? Whether is it possible to perform the extraction with the efficiency of 99% by doing only one extraction, or by doing multiple extractions? All these things will be coming to the picture in order to decide what is the extraction method we have to use. So let us discuss in detail different types of extraction methods we will employ in liquid extraction process. So you might have come across of using a simple separating funnel in the extraction process. Separating funnel is a glass apparatus. It is having a tap and it is having a stopper also. You will take the mixture which is needed to be subjected for separation process. You will dissolve the mixture in a suitable solvent and you will transfer the solution of the sample or solution of the mixture into the separating funnel. Then you will add required organic solvent into the separating funnel. You will shake the separating funnel for a particular interval of time, say it may be 20 seconds or 30 seconds or 60 seconds. Then you will keep the separatory funnel for equilibration. In this standing time, both the layers, they are organic and aqueous layers, will be getting separated. Then the layer which is present below to the upper layer will be transferred to another container. And here the lower layer may be organic layer or aqueous layer, whatever it is, and that is dependent upon the density. If the organic solvent you are using, it is lighter than water, then the organic solvent will be at the top of the aqueous layer. If the organic solvent is denser than the water, then the organic solvent will be at the bottom of the aqueous layer. Of course, you know this. So the extractions, what we do by using separating funnels, if you do only one extraction in order to extract the solute with extraction efficiency of 99%, then that extraction will be selective and efficient. With only single extraction, we can obtain the solute to be extracted to the maximum extent. Suppose if the transfer of solute from one liquid phase to another liquid phase is not possible to the maximum extent by doing only one extraction, then you may have to do multiple extractions by using lesser volumes of the organic solvents. Say, instead of using 50 ml, which you have used for single extraction of organic solvent, instead of using 50 ml of the organic solvent, if you use 10 ml of the organic solvent and you do the extraction 5 times. So instead of doing one extraction, which has yielded lowest extraction efficiency, you can repeat the extraction 5 times by using lower volumes of the organic solvent in order to achieve better extraction efficiency. These multiple extractions, which are very essential whenever the distribution ratio for the solute is very large. Distribution ratio is very large. Only single extraction will be yielding a quantitative extraction with more extraction efficiency. So even the distribution ratio is very large, if single extraction will not be able to yield maximum extraction efficiency, then we will go for multiple extractions by using several lesser volumes of the organic solvent. It may be 3 extractions or 5 extractions or 10 extractions. These extractions are usually done by using separatory funnel. So these type of extractions are called as batch extractions. So in batch extractions, we will use separatory funnel, and the aqueous sample solution will be transferred into the separatory funnel. Then the organic solvent will be transferred, will be taken, will be poured into the separatory funnel. Separatory funnel stopper is closed. Then it will be shaken for 30 seconds or 60 seconds. Then it will be made to stand. It will be made to be to the standby mode in order to equilibrate the two layers. Once the equilibration is done, you can release the stopper to collect the layer which is below to the upper layer. And this bottom layer may be organic or aqueous, that is dependent upon the density of the solvents you are using. So these type of extractions are commonly known as batch extractions. So batch extractions are liquid-liquid extractions which are performed by using a simple separatory funnel, where whenever it is not possible to perform the extraction with more extraction efficiency with best quantitative extraction, whenever it is not possible, then we will go for multiple extractions, and these extractions are called as batch extraction techniques. Okay, so these batch extractions are usually done by shaking the separatory funnel, and it is always preferred to use denser organic solvents than aqueous solvent, because when we do multiple extractions, we will be intended to collect the organic layer, we will be intended to collect the below layer. Once you transfer the sample solution into the separatory funnel, again and again we may have to add the organic solvent. So once the removal or discharge of the organic solvent after one extraction is over, we will be adding a fresh solvent, several milliliters of the fresh solvent into the separatory funnel. So let the organic solvent be settled at the bottom of the aqueous layer. Then the selective transfer of the solute from the aqueous phase to organic phase will be there. We can be expecting that. And because the density of the organic solvent is more than the aqueous solvent, it will be coming at the bottom of the aqueous layer. So it is very easy to collect the organic solvent once the extraction is over. So of course, if you are doing 5 extractions, say for example, from all 5 extractions, the organic layer will be settled at the bottom. Then that organic layer can be collected into a beaker, and if necessary, you can subject it for evaporation process or further investigation. That's what that batch extraction usually performed by using the organic solvent which is denser, which is heavier than water or heavier than aqueous solvent. And the other one is continuous extraction. This is in contrast to batch extraction. In the batch extraction, there is a requirement, that is, the distribution ratio must be at least 10 power 2 in order to do an extraction, in order to perform the extraction process, in order to selectively transfer the solute from aqueous phase to organic phase. The distribution ratio of the solute by using those two pair of solvents should be at least 10 power 2, means it should be 100. Then only the quantitative transfer of the solute will be possible to more than 98 or 99%. If you do only single extraction or multiple extractions, no problem. Even if you do quite a few number of extractions, the quantitative transfer of the solute will not be possible. So in such cases, we cannot prefer the batch extraction. So we will prefer continuous extraction. Continuous extraction means it is, as the name is implying, that it is a continuous process of extracting the solute from the sample. Sample will be taken in a condenser or in a extraction tube. Then the solvent will be taken in the solvent reservoir. Solvent will be heated in order to convert that into vapor, and the vapors of the organic solvent will be fetching to the aqueous sample solution. Then the vapors will be converted into liquid. Those liquids will take away the solutes which are present in the sample solution, and dependent upon the density, the organic solvent will be settled in the sample tube. Here we can use both lighter and heavier solvents when compared to aqueous solvent. So we will distill the organic solvent which is present in a reservoir flask. In continuous extraction, a continuous distillation of the organic solvent is involved. Once it is converted into vapor, it will be condensed back into liquid and it will be allowed to pass through the aqueous phase. So once the sample tube, which is containing the analyte, is filled by the organic phase, its capacity with respect to volume will be increased, will cross the limit, then the organic solvent will return back to the reservoir. So it will not simply return back to the reservoir, but also it will take the solute along with that. Here, mechanism is very simple because the solubility of the solute in the organic phase is more when compared to aqueous phase. The moment solute interacts with the organic solvent, the solubility of that solute will be seen in the organic solvent because the volume in the sample tube has been increased and there is a vent, there is a provision to pass the solvent once the liquid level rises because of the flow of the organic solvent into the sample tube. So that will come back to the reservoir. That will come back to the reservoir by taking the analyte. This process will be continuous. So we can do this. We can do this according to our requirement. How long the extraction process should be performed, whether 1 hour or 2 hours or 3 hours. I will show you one simple example how to do this continuous extraction process in the next slide. So this type of extraction is known as continuous extraction. Here we will utilize a sample tube which is provided with a condenser because the solvent after passing to the sample tube, it has to be condensed into liquid. First step is we will convert the solvent into vapor by heating the solvent which is present in the reservoir. Solvent reservoir will be fixed into a mantle, heating mantle, or a source of heat energy, and the vapors of the solvent will be made to pass into the condenser where the vapors will be converted into liquid, and liquid will pass through the aqueous sample solution. It is containing solute. Then the organic solvent will take out all those analytes back to the sample reservoir. This is a continuous extraction process. This type of extraction is very significantly required whenever the distribution ratio of the solute while performing the extraction by batch extraction method is less than 10 power 2. Even if the distribution ratio is less than 1 for some quite group of solutes, the batch extraction is not going to be unsuitable. In such circumstances, we will prefer continuous extraction over batch extraction. So continuous extraction is particularly useful whenever the value of D is less than 1. And even you perform 10 extractions or 25 extractions or as many number of multiple extractions if you do, the quantitative transfer of a solute from one phase to another phase is quite impossible. So in such cases, it is unscientific to say that it is unscientific to conveniently do such a number of multiple extractions. Say doing 100 number of extractions in order to extract 99% of the solute is unscientific. It is laborious because we will be using the organic solvent. Organic solvents are usually toxic, they are volatile, and some solvents will exhibit carcinogenic property. So we cannot expose ourselves to the organic solvent while doing the extraction process. Therefore, batch extractions are not preferred whenever more number of extractions are required to achieve required quantitative transfer of the solute. So these are the two circumstances. So when we prefer continuous extraction, the D value whenever it is less than 1 or multiple extractions are needed to be performed in order to extract the maximum amount of the solute, we will use continuous extraction technique. Here it is a simple apparatus, a simple equipment in order to demonstrate the continuous extraction, where here in continuous extraction process, we can take both the type of solvents. The organic solvent may be denser or lighter. Both denser solvent or lighter solvents we can use, but if you use lighter organic solvent, organic solvent will be at the top of the aqueous solvent. If you use denser organic solvent will be lower to the aqueous phase. So in this diagram, I have presented the continuous extraction equipment for extracting the solute by using denser organic solvent. So the solvent which is denoted by light orange color, it is denser organic solvent. That's what it is below to the aqueous phase. So this blue colored layer indicating the aqueous phase, which is having sample, and it is having the solutes which are indicated by the dot. Okay, sample reservoir has been connected to this condenser tube. This is the extraction tube, extraction assembly. And here into the extraction assembly, aqueous sample solution will be taken, and it has a provision. It has a provision for the passage of the vapors of the organic solvent through this particular vent, through this provision. And once the organic solvent come back, to the extraction tube, it will be transferred back to the solvent reservoir from this particular provision. Here is a stopper. We can make use of the stopper when to release the organic solvent or when not to release the organic solvent. All right. This is a simple instrument, simple equipment. Consider the solvent reservoir. Solvent reservoir is containing the solvent. And this has two provisions. One is outlet, another one is inlet. Outlet is for the solvent vapors. Inlet is for the condensed organic solvent in the liquid form after its interaction with the aqueous phase. Then it will come back to the solvent reservoir. So solvent reservoir, you place it in a heating source, heating mantle, or a hot water bath or sand bath, whatever it is, you place it. You start boiling the organic solvent. When organic solvent started to boil, it will be converted into vapor. Then the vapors will be going towards the condenser. Here, this is going to be the condenser. This upper tube is the condenser. Here, the temperature has been adjusted under room temperature, because this is the only reservoir getting heated and the condenser is not getting heated. So temperature in the condenser is maintained at room temperature because it has been fitted with the reflux condenser. Water cooled condenser will be fitted to this particular condenser above this. So all the vapors of the organic solvent will be converted into liquid here. They will condense back, the vapors will be condensed back into liquid, and they will come back to the condensed tube, the sample tube. Here it is containing the sample tube. So while they come back, they will interact with the solute which are present in the sample aqueous solution. If solutes are more soluble in the organic solvent, they will dissolve in the organic solvent and they will come to the bottom, because the organic solvent has the density more than the aqueous solvent. So the solute is carried by the organic solvent. It will come here. Once the liquid level is increased, let us open this tap. And this tap, sometimes it will be open, sometimes it will be closed. When the tap is closed, when the stopper is closed, we will work to open that stopper once the liquid level is raised. So we should not allow the liquid level here to rise above this, because if the liquid level is raised, the aqueous layer will also come into the sample solvent reservoir. So you must be very careful. So solute are carried by the organic solvent, and the organic layer will be settled at the bottom of the aqueous layer. So organic solvent will be released to the solvent reservoir, and now the solvent reservoir is with the solute. So you remove this sample tube and the condenser, you evaporate the solvent which is present in this solvent reservoir, procure the solute which has been extracted. So this is a continuous extraction by using organic solvent which is heavier than the aqueous solvent, which is heavier than the aqueous solvent. This is also a simple diagram, but two different diagrams are presented here for showing the continuous extraction process. For showing continuous extraction process by using the organic solvent which is lighter than aqueous solvent, that is water, and the organic solvent which is heavier than water. If the organic solvent is heavier than water, then the organic solvent will be settled at the bottom of the aqueous phase. That's what the provision for the organic solvent to go back to the reservoir is at the bottom. Here, the organic solvent is lighter than water. Therefore, the provision for the organic solvent to pass into the reservoir is at the upper side. This is also a simple equipment. This is a sample reservoir, solvent reservoir, where the organic solvent is taken. And the organic solvent will be heated in order to convert that into vapor. And the vapors of the organic solvent will pass here, and because this is a condenser tube and this condenser will reduce the temperature, therefore at that particular temperature the vapors of the organic solvent will be condensed back into liquid. So the condensed organic solvent which were entered into this condenser have been converted into liquid, and the liquid droplets will be made to fall into the funnel followed by a tube. And through this tube, the organic solvent will enter into the aqueous solution. Here exactly the aqueous solution is available. So organic solvent will interact with the aqueous sample solution. If there are any solutes extractable into the organic solvent will take out all those solutes. So because organic solvent is lighter than water, it will come up. So organic solvent, first evaporation takes place. The vapors of the organic solvent will be condensed back into liquids, and the organic solvent in the liquid phase will be made to pass into the aqueous phase. Then, because organic solvent is lighter than water, it will come up. Through this provision, organic solvent will come back to the reservoir by taking the analyte. So analyte has been collected in this particular reservoir back. So organic solvent without analyte has been used to perform the extraction. Then once the continuous extraction process is completed, solutes have been transferred into the organic solvent. So this type of provision, while making outlet at the upside, it is to collect the organic solvent which is lighter than water. This is vice versa because the organic solvent is heavier than water. So same thing, organic solvent will be evaporated in order to convert that into vapor, and the vapors will be condensed back into liquids, and the liquids will pass through the aqueous sample solution which is present in this tube. So certainly two layers are going to be formed because organic solvent is heavier than water because of its highest density. It will be settled at the bottom. So organic solvent which are collected at the bottom will be passing into the solvent reservoir back. So first vapors of the solvent, then it will pass through the aqueous sample solution, and it will take out all those solutes which are having relative solubility in that, and the solution of solute and the organic solvent will come back to this reservoir. So that's what this is, a continuous extraction. So both we can use organic solvents which are heavier than water or lighter than water. Only thing is, if you use heavier organic solvents, you have to give the outlet at the bottom. If you use lighter organic solvents, you have to give outlet at the top. So this is also same pictures I have presented here. And here the organic solvent which is lighter than water. Here the organic solvent which is heavier than water. So you can see here, solvent reservoir is having solvent and it is heated to convert the solvent into vapor. And the vapors of the solvent will be condensed back into liquids, and that liquid will come through this funnel and followed by the tube. And the organic solvent in the liquid state will interact with the aqueous phase. Here it is represented by the arrow. Then it will come at the top because it is lighter solvent. It is lighter solvent. Once the liquid level is raised by passing more volume of the organic solvent, that will start to come back into the solvent reservoir. So analyte has been procured into the organic solvent. Analyte has been extracted. But here, organic solvent has been heated in order to convert that into vapors and then droplets. Droplets will be coming to the sample tube, which is having a sample solution, and it will interact with the sample solution. Because its density is more, organic solvent's density is more, it will be below to the aqueous sample solution. It will be below to the aqueous sample solution. So this is how we can use. Here there is a separate tube. There is a separate tube to collect the organic phase, or in the previous diagram, whatever the provision has been made, that can also be followed. Both are same here. Both are same. Here there is a funnel in order to convert vapors of the organic solvent into liquid. Then the liquid will be collected into the funnel followed by this tube, and where the vapors of the organic solvent will be coming up because they are lighter. So when compared to this, the previous equipment what I have showed is better here. If the organic solvent is denser, this type of equipment will be used more commonly. So this is a slide which is indicating the type of apparatus we will use in order to perform continuous extraction by using lighter organic solvent and denser organic solvent. Here I will show you a video in order to illustrate how the continuous extraction process will be done. So continuous extraction, you know the definition. It is an extraction technique when our D value is less. You can see here, this is the sample tube and this is the water cooled condenser. This is the solvent reservoir. And in this solvent reservoir, solvent has been taken and it has been kept in a heating mantle. So it is heated. It is heated. The vapors of the organic solvent are going towards the sample tube. Here you can see the vapors are going here and it is coming back to the aqueous sample solution. This is the aqueous sample solution. So this is to collect the sample which is lighter. Whenever lighter solvents are used, this type of funnel will be used. So solvent is condensed and in the liquid form that will be reaching to the aqueous phase. All right. So this is how the continuous extraction will be done. So continuous extraction is a process in which the solutes are going to be extracted continuously. Solutes are having lesser distribution ratio, that is the value of D less than 1. Whenever the batch extraction is not possible to use, In order to quantitatively extract the solute, either by doing single extraction or multiple extractions, we may have to use continuous extraction. So continuous extraction is always advantageous whenever if we wanted to extract the solutes in minute quantities. Let us move on to the applications of solvent extractions. Whatever you use, either batch extraction or continuous extraction, they are applicable for extracting the solutes which are present in different origins. And not only for the extraction is because to isolate a single chemical species, if you take a complex mixture, if you take a sample, and we will be intended to isolate one individual species in that particular sample. So the isolation of the single chemical species will be possible, of course, by liquid extraction technique. Sometimes if you take the sample where the volume will be 1 liter, if you prepare a sample solution of 1 liter, where only 1 milligram of the solute may be present, you can take that 1 liter of the sample, aqueous sample solution in the extraction instrument, and you can extract with say 10 ml of the organic solvent. So 1 milligram of the solute which was present in 1 liter of the aqueous phase can be certainly transferred into 10 ml of the organic phase. So 1000 ml to 10 ml. Almost 100 times the concentration has been increased for the solute. So 1 milligram of the solute was present in 1 liter of the aqueous sample solution. Once you perform the extraction, assume that 1 milligram of the solute has been extracted into the organic phase, which has the volume of 10 ml. So 1000 ml to 10 ml, that is 100 times the concentration has been increased. So concentration of the solute is possible by extraction. So concentrating trace quantities. Many metals, as I have presented while discussing the extraction of essentially covalent neutral molecules, ion association complexes, and uncharged metal chelates like this. Many metals can be converted into complexes. What are these metals? They are present in inorganic species. Not only the metals, even organic materials can also be subjected for liquid extraction. I will show you some examples what kind of organic compounds can be used for extraction process. So metals in the form of uncharged metal chelates or in the form of ion association complexes, they can be extracted into the organic phase. And even organic compounds can also be subjected for liquid extraction, where we will encash acidity or basicity of the organic compounds while performing the extraction process. And in more particular, metals are going to be extracted, and the extracted metal will be subjected to react with certain reagents, because we know some metals will react with the reagent and will produce the colored systems, colored complexes or colored products. And the absorption of these colored products or colored complexes is proportional to the concentration of the metal. So solvent extraction is not only a simple separation technique, it is very useful in concentrating the metal, and it will also assist in the quantification of the solute more accurately. We don't lose even very less quantity of the solute. This is going to be highly accurate technique. So these type of extraction procedures are quite useful for determination of concentration of metals by forming them into colored systems, especially in the analysis of metallurgical samples or geological samples, petroleum products, foodstuffs, plant and animal tissues, and even body fluids. Not only the metals, any material, any solute, any analyte which is questionable, which you are intended to determine its quantity, they can be subjected for liquid extraction. We can say, for example, urine sample you take or blood you take. Suppose we are interested to determine the quantity of urea present in urine, or urea present in blood, or uric acid present in blood, or creatinine present in urine. We have to separate all those endogenous substances. How to do this? By solvent extraction. Therefore, solvent extraction is going to be very useful technique. And in some cases, if there are multiple metals are present, especially in metallurgical samples, there are multiple metals are present in a sample, we have to avoid the other metals apart from the analyte which are present in the sample in order to accurately determine one metal which is under interest. Otherwise, the other metals are also going to interfere. So this is what the liquid extraction process is very, very important with respect to its application. And even hydrocarbons, acids, fats, waxes, they can be isolated. Of course, their amounts may be lesser. Their quantification will be done by using other sophisticated techniques such as chromatography or mass spectrometry, etc. The isolation of the single chemical species from such samples is very important, and this will be done more significantly by using solvent extraction technique. Of course, it may be by performing batch extraction or continuous extraction. So solvent extraction is a very important technique in order to isolate a single chemical species from the complex mixture, in order to concentrate trace quantities of the analyte, in order to determine the metals as minor and trace constituents in variety of inorganic and organic materials, and even in order to isolate the organic compounds from various complex mixtures, in order to determine metals concentrations by forming them into complexes with a suitable ligand, and extracting that metal complex into the organic phase and measuring the intensity or absorbance of that colored species by spectrophotometry, and even isolation of single chemical component uh, such as in hydrocarbons, waxes, acids, fats, etc. So all these are important applications of liquid extraction. Some examples I am going to present here. I will give you a mixture containing benzene and other liquid that show better solubility in water. I will ask you to separate how to do this. So you have two components, benzene and other liquid. Other liquid solubility in water is more, but benzene has no solubility in water. So you can separate. So here benzene is an organic species, organic compound, and the liquid, because it possesses the solubility in the aqueous solvent, that is water, that liquid will be aqueous species, aqueous compound. So benzene, in the presence of that liquid, you take it in water, you shake it in a separating funnel. Benzene will be above the water layer, and the liquid which is having the solubility in water, which will come into water. So that liquid has been separated from benzene. So here, the polarity of the liquid which is present along with the benzene is more. That's what it has showed solubility in water. Here, like attracts like principle holds good, like dissolves like principle holds good. The aqueous solubility of the other liquid is more when compared to benzene. Benzene is insoluble in water. So benzene has been separated from liquid. So what is that liquid? That has been transferred into water. So benzene and water here, they are two different liquids. One will be organic and other one will be aqueous. Benzene is having lower density and water is having higher density. So water will be used to procure the other liquid present. So therefore, polarity, the first factor. Second factor is the density and immiscibility. Benzene and water, they are two immiscible liquids. They are not mixed. One is not dissolved in other, right? So benzene will form its own layer above water because of its density and its immiscible nature. So therefore, we can easily separate benzene from a liquid, any liquid which shows solubility in water. I will tell you another important example, very common example, separation of oil from water. You are very familiar about the oils. Whatever the oil you take, either you take petroleum oil or any edible oil, these oils are immiscible with water, right? And they possess density lower than water. The density of oils will be lower than water. If any oil is mixed with water and given to you, how to separate? You take the mixture, transfer into separating funnel, shake it, equilibrate both the layers. The upper layer will be oil, lower layer will be water. So run the water, collect the oil layer, which is above the water, which was present. So oil is simply separated by water. So oil is separated from water. So this is how the separation of oil from water will be done. Here the separation follows immiscibility and density. Immiscibility means oil is immiscible with water. It is not soluble in water. And oil is lighter than water. It is a lighter species than water. Its density is lower than water. Therefore, it will be at the top of water layer. Therefore, we can separate oil from water. Let me take one practical example here for separation of 4-chloroaniline, benzoic acid, and 1,4-dibromobenzene. If you are given the mixture containing 4-chloroaniline, benzoic acid, and 1,4-dibromobenzene, as a routine analysis, as a routine separation process, the synthetic laboratories have to adapt the principles of these liquid-liquid extraction techniques. So in that context, this example will be very, very significant and highly useful. Here, it is a ternary mixture. 3 compounds are present in the mixture: 4-chloroaniline, benzoic acid, and 1,4-dibromobenzene. These 3 compounds are possessing different properties. 4-chloroaniline is basic because it has amino group. Benzoic acid is having carboxylic acid group, therefore it is acidic. C6H5COOH, it is acidic. Because of the presence of carboxylic acid, it is acidic. And dibromobenzene, 1,4-dibromobenzene, it is neither acidic nor basic. Electronegative bromine have been substituted in place of hydrogen. It is neutral. It is neutral. So this acidic, basic, and neutral property of these 3 compounds are encased in the separation of these 3. Very simple. You take the mixture in a separating funnel, you pour the mixture into the separating funnel. Let us take ether as the organic solvent. Ether as the organic solvent. So you take the mixture and transfer the mixture into the separatory funnel, and into the mixture you add hydrochloric acid. You acidify the mixture by the addition of excess of hydrochloric acid, say 5% hydrochloric acid you add. After the addition of hydrochloric acid, you know basic chemistry here, because this is basic. This is basic. NH2 is basic. This will undergo protonation in order to get converted into NH3 plus. NH3 plus. 4-chloroanilinium chloride you will get. 4-chloroanilinium chloride. So this is water soluble. This was water insoluble. Once you add hydrochloric acid, dilute hydrochloric acid, say 5%, is prepared by using water. Now the separatory funnel is also having water. It's also having water. You may take water initially, or after the addition of HCl, water will be introduced. So 4-chloroaniline has been converted into 4-chloroanilinium ion. So this is water soluble. So after the addition of HCl, you shake separatory funnel. After shaking this, you make it standby, during which this positively charged 4-chloroaniline will be easily transferred into aqueous layer, because it is easily soluble in water. It is easily soluble in water. Now the organic phase is left with acidic benzoic acid and 1,4-dibromobenzene. 1,4-dibromobenzene. You release the aqueous layer. Aqueous layer is 4-chloroaniline under protonated form. You release this. You release this. Then you treat with base. You treat with the base. You recrystallize it. So you will get 4-chloroaniline back. Now it has been separated by the mixture, and it is free from acidic benzoic acid and 1,4-dibromobenzene. Now 1,4-dibromobenzene and benzoic acid are present in the organic layer. They are ether soluble. Okay. Now the organic solvent, organic layer is having two compounds, benzoic acid and 1,4-dibromobenzene. To the organic solvent, you add aqueous solution of sodium bicarbonate in the next step. Once 4-chloroaniline is separated, you release the aqueous layer. Now separating funnel is having left with only organic phase. To the organic phase, you add say around 10% of sodium bicarbonate. Shake it. Around 10 ml or 15 ml or 20 ml bicarbonate you add, shake it. Sodium bicarbonate is a weak base. Simple reaction between benzoic acid and sodium bicarbonate takes place. So benzoic acid will be converted into sodium benzoate. Sodium benzoate is ether insoluble, but it is water soluble. So sodium benzoate will be coming to sodium bicarbonate layer now. So benzoic acid has been separated from 1,4-dibromobenzene. So aqueous layer again, it is containing sodium benzoate. You release it out, treat with acid, convert sodium benzoate into benzoic acid, purify it, recrystallize it. Now the organic layer is containing 1,4-dibromobenzene. Evaporate the ether, collect 1,4-dibromobenzene. Very beautiful application of the liquid-liquid extraction technique. So like this, even you can use liquid-liquid extraction technique for the separation of organic compounds which are acidic, they are phenolic, and even they are neutral. If you assume you have been given a mixture containing acidic, phenolic, and neutral organic compound, you take it in a separating funnel. To the separating funnel, add excess of sodium bicarbonate. Sodium bicarbonate will react with acid. To convert acid into sodium salt. So aqueous layer is containing acid. Release the aqueous layer, neutralize it, you will get back the acid. Now the acid has been separated from phenol and neutral organic compound. Next, organic layer, say ether or carbon tetrachloride or chloroform, whatever it is, or dichloromethane. It is containing phenol and neutral organic compound now. You add excess of NaOH to the extraction process, you introduce NaOH. Phenol is acidic, NaOH is basic. NaOH is a selective reagent to react with phenol to produce sodium phenolate. So sodium phenolate is aqueous soluble, organic insoluble. So after the addition of NaOH, you shake the separatory funnel. Phenol will be converted into sodium phenolate, and that is water soluble. It will come to aqueous layer. Neutralize sodium phenolate by the addition of water. Convert phenolate, sodium phenolate into phenol. Recrystallize it. Over. Now the organic layer is left with only neutral compound. Evaporate the organic solvent, you will get neutral compound. So neutral compound, phenolic compound, and acidic compound can be easily separated by using this liquid-liquid extraction technique. This is also one of the important examples for the separation of three compounds which are present in a mixture, namely cinnamic acid, paratolidine, and anisole. Cinnamic acid is acidic. Paratolidine is basic because of amino group. Anisole is quite a neutral compound. Again, you take the mixture in the separating funnel. Because all these three compounds are soluble in dichloromethane, you dissolve the mixture in dichloromethane, transfer the solution of these three compounds or mixture in dichloromethane into separatory funnel. Add hydrochloric acid, aqueous hydrochloric acid, say 5% hydrochloric acid, you add 10 ml. Now the volume of aqueous phase is 10 ml, it is containing hydrochloric acid. Again, hydrochloric acid will react with the base because carboxylic acid will not react with hydrochloric acid, or anisole will not react with hydrochloric acid. So only the reactant to react with hydrochloric acid is 4-methyl-aniline or paratolidine. So paratolidine will be converted into 4-methyl-anilinium chloride. So this is extractable to aqueous layer. First aqueous layer is containing paratolidine in the protonated form. This is aqueous soluble. So you take the aqueous layer, release out from the separatory funnel, add NaOH to neutralize excess HCl, and convert this protonated paratolidine into paratolidine purified by crystallization. That's it. So paratolidine is separated from these two compounds. Now the organic layer is left with anisole and cinnamic acid. Take the aqueous layer, organic layer, dichloromethane layer you collect. You add excess NaOH, strong base you add. Simple neutralization reaction, acid-base reaction between cinnamic acid and NaOH takes place to produce sodium cinnamate. Sodium cinnamate. Sodium cinnamate is soluble in aqueous layer, insoluble in dichloromethane. So aqueous layer is containing now the excess of NaOH and sodium cinnamate. You neutralize this excess of NaOH by the addition of HCl. Then HCl will also convert the sodium cinnamate back to cinnamic acid. You purify this. So first aqueous layer was used to obtain paratolidine. Second aqueous layer was used to obtain cinnamic acid, and the organic layer, dichloromethane layer, is left with anisole purified by distillation. Very beautiful example, you know. So liquid extraction is very useful, very useful technique. Another beautiful example I am presenting here. Let you assume 4 compounds are present in a mixture. The sample which is going to be given you is containing 4 compounds: phenol, 4-ethyl benzonitrile, 4-ethyl benzonitrile, or 4-ethyl cyanobenzene. Cyanobenzene or benzonitrile, both are same. 4-ethyl cyanobenzene or 4-ethyl benzonitrile, methyl amino cyclopentane, right? So this is propanoic acid, 3-phenyl 3-methoxy propanoic acid. 1, 2, 3. 3-phenyl 3-methoxy propanoic acid. So you have a mixture of 3-phenyl 3-methoxy propanoic acid, methyl amino cyclopentane, 4-ethyl cyanobenzene, and phenol. You have to separate this. Take the mixture, the solution of mixture in dichloromethane, and transfer into separating funnel. You add HCl, say around 10%. You add HCl. HCl is strong acid. So there must be a base. There must be a base to react with the acid, because acid will not react with the acid. Phenol will not react with hydrochloric acid. Cyanide, benzonitrile or cyanobenzene will not react with hydrochloric acid, and this is the only compound. So if you add hydrochloric acid, there are 2 layers. One is dichloromethane layer and aqueous layer of hydrochloric acid. Hydrochloric acid will be selectively reacting with this methyl amino cyclopentane to convert that into methyl aminium cyclopentane chloride. So this is present in the aqueous layer. Release the aqueous layer, add excess of base, purify by crystallization. You get back this. So in one shot, you have separated 1 compound from other 3. Take the organic layer, dichloromethane layer. It is containing phenol, 4-ethyl cyanobenzene, and 3-methoxy 3-phenyl propanoic acid you have now. So this is the acid. This is strongly acidic than these 2. You add mild base, that is sodium bicarbonate, say around 10%. What will happen? These 2 are not reactive with sodium bicarbonate. Only propanoic acid derivative is reactive. So this will be converted into sodium carboxylate. So sodium propanoate, 3-methoxy 3-phenyl sodium propanoate is going to be formed. This is water soluble, aqueous soluble. So this will be transferred to aqueous layer. You release the aqueous layer, acidify it by adding excess of hydrochloric acid, and purify. You will get back your methoxyphenyl propanoic acid. Then in the organic layer, still 2 compounds are present: cyanobenzene and phenol, 4-ethyl cyanobenzene and phenol. Phenol is slightly acidic than 4-ethyl cyanobenzene. In the organic layer, phenol and cyanobenzene are present. Now, to the organic layer, you add either NaOH or KOH. Strong base you have to add. Phenol will not react with sodium bicarbonate. It has to be reacted with strong base to convert that into sodium phenolate or potassium phenolate. So when you add KOH or NaOH to the organic layer, aqueous layer is going to be formed. When you shake it, phenol will react with NaOH to form sodium phenolate, or if you have added KOH, potassium phenolate is going to be formed. So now the aqueous layer is containing phenolate ion, a sodium phenolate or potassium phenolate, and the organic layer is left with only ethyl cyanobenzene. So you neutralize this by the addition of acid, purify it, you can use, right? Say methyl aminocyclopentane, phenyl methoxypropanoic acid, ethyl cyanobenzene, and phenol. They can be easily separated by this beautiful application, by beautiful example. I have illustrated how to separate these four compounds. So like this, whether the sample is containing 1 or 2 or 3 or 4 compounds, you can easily separate them, provided what are the reagents you have to use must be known to you. And this is also a same example for showing the separation of phenol, benzoic acid, aniline, and benzene. So take the organic layer in dichloromethane, treat with sodium bicarbonate. Sodium bicarbonate will react with benzoic acid to produce sodium benzoate, and this will come to aqueous layer. You treat the aqueous layer with HCl to get benzoic acid. Take the organic layer, left with 3 compounds. There is aniline, it is basic, and phenol, it is acidic, benzene, it is neutral. Add sodium hydroxide. If you have added sodium hydroxide, phenol will be converted into sodium phenolate, that will come to water layer. The organic layer will have left with aniline and benzene. Add hydrochloric acid to the organic layer, extract it. Aniline will be converted into anilinium ion, protonated species. It is aqueous soluble. Release the aqueous layer, treat with NaOH, get back aniline. And organic layer is left with benzene. So evaporate the organic solvent, you will be ending up with benzene. So like this, 4 compounds can be separated. With respect to their properties, we can use suitable solvent. So this is a general chart I am going to present. You take the compounds which are basic, acidic, and non-basic and non-acidic. They are neutral. How to introduce the separation? Our separation process. If you take the mixture of these 3 group of compounds, if you add base, means if you have raised the pH of the solution greater than 13, that is up to 14, you have raised the pH, neutral compounds will be left over as such, because bases will not react with neutral compounds, because you have added base will be reacting with only acidic compound. So acidic compound will be converted into salt. The salt will be water soluble. So neutrals have been separated from acidic compound. If you add acid, say if you lower the pH to 1, bases will be protonated and they are separated from neutral and acidic compound. Here basic and neutral compounds have been separated from acidic compound after the addition of base. If you add acid to the separation funnel and you extract, base will be protonated and it is separated from neutral and acidic compound. So accordingly, you can build up the separation procedure in order to successfully separate the compounds from the mixture. So these are about certain examples for showing the application of liquid-liquid extraction. I told you determination of concentration of metals in real samples will be done by utilizing the principle of solvent extraction. One such example I have presented here, determination of lead in polluted water. Usually lead will be present in trace quantity. So we will commonly employ determination of lead by spectrophotometric technique. So in spectrophotometry, we will utilize a chemical reaction, very popular chemical reaction, that is lead will react with dithiazone, diphenyl thiocarbazone, to form lead dithiazone complex. This lead dithiazone complex is measurable between 520 and 545 nanometer. So you prepare the standards containing lead, add known excess of dithiazone to obtain complex of lead dithiazone. Of course, this is chloroform soluble, water insoluble. Take the aqueous sample solution containing lead, acidify it by the addition of 1 molar HNO3, add excess of diphenyl thiocarbazone in chloroform. Diphenyl thiocarbazone must be made alcoholic. You have to add some volume of alcohol here in order to stabilize dithiazone. Diphenyl thiocarbazone is dithiazone. You shake the separatory funnel. You take this mixture in a separatory funnel and you shake it. The chloroform layer will be pink in color due to lead dithiazone complex. This is the lead dithiazone complex. Its stoichiometry is 1:2 with respect to lead and dithiazone. So the absorbance of lead dithiazone complex at 520 to 545 nanometer is proportional to concentration of lead in water. So spectrophotometry will utilize liquid-liquid extraction. The lead which was present in the aqueous sample has been extracted into chloroform with dithiazone. By extracting lead with dithiazone into chloroform, a colored species has been obtained. So this is how the concentration of metals can be determined by spectrophotometry. But prior to spectrophotometric determination, liquid-liquid extraction technique will be employed. Here is some other example I have presented. One is determination of beryllium using acetylacetone by UV spectrophotometry. The complex of beryllium acetylacetone will act as a chelate to produce a neutral chelate of beryllium acetylacetone, which is extractable into chloroform, and that could be measured at 295 nanometer. So whatever the absorbance at 295 nanometers due to beryllium acetylacetone complex, because it show absorption maximum at 295 nanometer. And similarly, determination of boron by using ferrine. We know a general chemical reaction between boron and salicylic acid. 2 moles of salicylic acid will react with boron. Boron is trivalent and pentavalent. Here, trivalent boron is utilized by salicylic acid to form a complex. And the residual charge is -1 here. So bis salicylatoborate 3. This is bis salicylatoborate 3 or borodisalicylate. 2 moles of salicylic acid reacted with boron in order to form 1 mole of borodisalicylate. This is not neutral. This is negatively charged. So in order to extract this into organic solvent, you have to neutralize this charge. How to do this? You need a counter reagent which is having positive charge. Ferrine is a positively charged complex, metal chelate. It is having 2 plus residual charge. So 2 moles of this borodisalicylate you take and treat with 1 mole of ferrine. 2 moles of borodisalicylate plus 1 mole of ferrine, you will get 2 moles of bis salicylatoborate or borodisalicylate ferrine ion association complex. These were chloroform insoluble, but this ion association complex is chloroform soluble. This is colored system. So 512 nanometer will be the wavelength of maximum to measure this ferrine bis salicylatoborate 3 ion association complex. Here, borodisalicylate is negatively charged species, ferrine is positively charged species. Ionic aggregate of borodisalicylate and ferrine is formed as ion association complex. So 512 nanometer, right? Somewhat orange colored complex is produced. Ion association complex will possess some deep orange color measurable at 512 nanometer. So the absorption at 512 nanometer corresponds to concentration of boron in any sample. So this is how the extraction principle has been utilized to extract the ion association complex into chloroform, and thereby we can determine the concentration of boron. So like this, several examples we can quote in order to show the application of liquid-liquid extraction. So these are all about some general applications of liquid-liquid extraction. So in this module, we have discussed about methods of extractions. They are batch extraction and continuous extraction, and some general aspects, general applications of liquid-liquid extraction we have discussed. So thank you very much for your patience. We'll see you in the next module.